李弘毅，对啊，我有看他的 YouTube， 他的 machine learning 的那个课程，他甚至有在其他地方演讲，台大那个什么。Okay, almost the end of. You already did it? Okay. Okay, we're almost to the end of the tournament. This will be the last stage of this afternoon's fight. So the problem is set, topic number 3. And the reporter, you have 5 minutes to prepare for your presentation. And I also like to have a reviewer and opponent to write down the name of the presenters. Okay, reporter, please take the floor.
So, good afternoon to honorable judges and fellow contestants. Today I'm going to present problem number 6, non-contact resistance. So here comes the problem statement. The responses of a LRC circuits driven by an AC source can be changed by inserting either a non-magnetic metal rod or a ferromagnetic rod into the inductor coil. How can we obtain the magnetic and electric properties of the inserted rod from the circuit's responses? And our main focus is on the electric and magnetic properties of the inserted rod. So since it was mentioned by the problem statement, so let's give LRC circuits a simple introduction. So as you can see here, the L stands for the inductance, and R stands for resistance, and C stands for capacitors. So here comes our theory model. So this equation finally symbolizes the impedance in this RLC circuits. And so here is the value of the impedance. So by this equation, we can get the relation between the voltage and the current and the resistance. So here's our another theory model. So this page is about the inductance of a cylindrical air core coil. So as you can see right here, the R stands for the radius of the coil, and the N stands for the number of turns in wire coil, and mu stands for permeability of core material, and A stands for the area of coil, which equals to pi r squared, and finally L stands for the average length of the coil. So here's our I'm going to talk about important information is that when we insert a ferromagnetic rod into RLC's inductance, which means insert the rod into the coil, and the eddy currents will be generated, and which means that will cause reluctance in the system, and this can simplify as resistance in the circuits. So I think the explanation of this matches the problem statement's name, non-contact resistance. So to know the relationship between the inductance and other parameters, we first simulate the circuits. So first simulation, we got our independent variable as inductance from 1 to 50 and 100. And control variable is the capacitance and resistance and frequency. So as you can see here, when we increases the inductance, the amplitude of the current would simply decrease, and that's the relationship between the inductance and the whole system. So try to introduce the experiment in reality. So here's our experiment setup. We use sweep function generator and digital storage oscilloscope and inductance, capacitor, and resistance. So here comes the experiment 1. And the independent variable is the inductor, which we have two kinds of inductors value. These two values. And the dependent variable is the amplitude of the wave of voltage. And the control variable is the frequency, resistance, and capacitance. So by the equation here, we can get the value of the the value of the inductance here. So from these two data, we can find out that larger inductance values will have a smaller amplitudes of voltage, which means the change of the voltage will be smaller. So, in the experiment 2, in this experiment, our independent variable is the rod inserted, and we chose four types of condition. The first one is none, and then we inserted copper ferromagnetic, and that is magnetic rod. And the dependent variable is also the amplitude of the wave of voltage, and the control variable is the same as experiment 1. So you can see here that if we inserted a copper rod to the coil, since copper rod is a non-magnetic rod, so the inductance won't have any change. So the amplitude of the voltage is exactly the same. And here is we inserted nothing to the coil compared to ferromagnetic rod inserted. So there's an obvious difference from the amplitude of the voltage. The first one is 1.42 volts, and the second one is 1.38 volt. And here's the third part of this experiment, that we insert the magnets into the coil, and we discovered that copper is quickly repelled by magnetic field, and ferromagnetic rod is attracted to magnetic field since the change of the voltage. And the third experiment, we control the magnetic length inserted in the coil, and the dependent variable is also the amplitude of the wave, and control variable is frequency, resistance, and capacitance. So here's the result. First, we inserted nothing to the coil again and get the same value of peak-to-peak voltage. And next, we inserted a magnets, part of the magnets, and we get a different value of peak-to-peak voltage. And also the induction was changed due to the magnets. And from these two charts, and we can see that as the inserted length of the magnets increases, and the inductance first increases as well, and the peak-to-peak voltage keeps decreasing. So yeah, that's what we get from our experiment 3. So here's the conclusion of problem 6. So amplitude of wave of voltage is influenced by inductance of rod inserted. Second, and the bottom 3 is what we get from our 3 experiments. So air neither attracted or repelled by magnetic field, and copper since the permeability of the original is bigger than the copper one, so it will weakly repelled by a magnetic field. And last but not least, magnetic and ferromagnetic will be strongly attracted by a magnetic field. And that's all. Thanks.
Okay, thank you. I'd like to have an opponent ask some questions.
My first question is, have you observed the metal rod will be shaking when you put it into an inductor?
Sorry?
Will the metal rod be shaking when you put it into the inductor?
So we make sure that the rod is inserted into the
So
coil.
no shaking.
No shaking.
Okay. Okay. So what do you think that the magnetic field in the inductor will be all the same like from in the whole inductor? Will the magnetic field be the same at every point?
No.
No. Do you think an inductor with a metal rod can be equivalent to an empty inductor and a resistance?
Pardon?
Do you think an inductor with a metal rod can be equivalent to an empty inductor with a resistance?
No.
No. Okay, so do you think there's a phase change after the inductor, after you put the metal rod in the inductor?
You mean compared to the original coil without anything?
Yeah, do you think the phase between voltage and current will change?
Yeah. Yes.
You think it will change? Do you try to insert on the video? Thank you.
Okay, thank you. Preparation time for the opponent. Opponent, please be ready. Okay. Opponent, please take the floor.
Hello everyone, my name is TYPT from PF5, and today I'm going to oppose problem number 6, non-contact resistance. And here is our problem statement. And about this problem, we'll be mainly focused on the relationship of different material and experiment results, and how does the raw number affect the result, and how the AC frequency affects the result. And overview of the report. About the theoretical model, let's talk about the relationship between current, voltage, and resistance, and talk about AC current. And for their concepts, they didn't have the explanation of the theory. And for experiment and setup, they put inductors, rod insert, and magnetic lens inserted in the coil. And their pros is they use simulation to explain this phenomenon. But their cons is they didn't consider other forces that affect in real situation. For example, magnetic field. And for the data analysis, they talk about peak-to-peak simulation. And their cons is some parameters stack of data points and didn't put all of the data chart of different material to compare the result. And also, they didn't really explain clearly about how you will do the experiment when they are explaining the data. And for our discussing points, for our theoretical model, we'll also be talking about the relationship between current, voltage, and resistance, and also added current. And I'm going to talk about whether the metal rod will shake or not, and what causes this phenomenon to happen. And the magnetic field will change after we put metal rod inside the inductor. And for experiment and setup, we also want to talk about inductance, rod insert, and magnetic lens inserted in the coil, and also about electricity part. And for the point, and we want to talk about experimental setup, like make it more clear because I don't think it really clarify this part, and how to calculate the electricity and magnetic field. And for data, I also want to talk about peak-to-peak simulation, and I'm going to talk about the difference between theoretical value and their experimental data. Thank you. And I want to invite.
Please proceed for the discussion.
So, let's come to the theory part. Yeah, this part. I don't really understand what this part is, but can you explain it again?
So there's two equations stands for the value of the voltage and the current.
Which part? I mean the voltage of
The whole system. And from here you can see that it's just it's alternating to get what we want for calculation.
So the V on the left side is also going to be for the whole system, or is the
Yes, it's the same.
It's the same. So this part you are just calculating.
So from this we get the impedance of the inductor and the capacitor, and we can calculate it into this equation so that we can get the relationship of the current, the voltage, and the resistance, and the inductance, and even the frequency of the relation between them in this RLC circuits.
Okay, and then what's the V there stands for?
As I mentioned here, this stands for impedance.
What's impedance?
Impedance is kind of like the resistance of the circuits, but yeah, that's it.
Okay, then in the short question time, you say that you didn't observe the metal rod will be shaking. I'm not saying that it is an experimental value. It's like, have you noticed this phenomenon will happen?
No, because we focus on as a problem statement. We focus on the magnetic and electric properties of the rod. So what we do is observe the value of relevant parameters and compare them.
And the reason why I will ask that is because if the magnetic field change in your inductor, then because if you put ferromagnetic thing inside, they will be kind of like an electric magnet. So because the Lenz's law will happen, so that's why I think if you put a metal rod inside the inductor, it will be shaking. So you didn't observe this phenomenon.
Yes.
Okay. And about page 9.
Which one?
So can you explain again? Because you jumped really fast about this graph. No, page 9. So you are trying
So in this simulation, we change the inductance value, and what we get is that as the inductance increases, the amplitude of the currents, which means the change of the currents it gets smaller.
Change of the current gets smaller.
So like because we are using this as a purpose statement, this RL series circuit is driven by AC source. So that's the phenomenon that we can observe in the experiment simulation.
Okay, and my question is, what is the difference between this graph and this graph?
So you have to see the value right at the bottom of this page.
So the value is not shown in the graph.
So if you see clearly, there's a difference that the peak to peak is different from the other one.
So also you're saying that the peak to peak this part is the distance is smaller.
Yeah, that's what I mean.
Okay. And page 22. You say you insert two-thirds of the magnet inside. And my question is, how do you put just two-thirds of the magnet? So there are like a part of the magnet that is outside of the whole inductors.
So we first measure the length of the magnets, and as we insert it, we measure what length we want to insert.
So my question is, so are there still a part of magnet outside of the
Yes,
inductor?
yes.
So don't you think if there is a magnet outside the inductor, it will affect the result, it will affect the magnetic field?
I think that's not. It may concern. There might be some interesting phenomena, but that's not what this problem statement is looking for.
So you don't think that will affect the thing on the problem statement is saying you have to calculate the magnetic thing? You don't think that will affect? So nothing will change, even though there are a part of magnet outside the whole inductor.
There might be something changed, but what we focus on is only the value and the parameters.
Okay. Then page 19. What do you mean the ferromagnetic rod is attracted to the magnetic field? It's like it's what you put the thing inside the inductor, right?
Yes.
Then what is the attractive part happen?
So this is kind of a solution of it, and so as we mentioned in this part, when we change the inductance, so the permeability of the coil will differ, and that causes the change of the magnetic field and cause what
I know, yeah, but
how do I see?
what is attracted to the magnetic field? Like it was staying on the inductor or something? What is being attracted to?
Sorry, I don't understand.
Okay, next question, page 13. Okay, and my question is, what's this part?
So it's a little similar for as this part, but in this part the value we focus on is the peak to peak voltage, and what we change the inductance, and from this graph we can get that larger inductance values have smaller amplitudes of voltage.
Okay. Next question is, what is the main factor caused different
So, as I mentioned here, it's not only a ferromagnetic rod, and as long as it is conductivity, when you insert the item into RLC circuits, inductance, eddy currents will generate inside the coil, and that causes reluctance, which you can understand as kind of resistance to all the system.
Okay, I understand. And I only see you estimating the voltage. And my question is because the problem system is there are L and C three parts in the whole circuit. So after you put the rod inside the inductor, what will happen to the other two?
The other two parts.
The other two, the capacitor and the resistance. Is there going to be any change with the two?
So as the problem statement says, so the main value will be observed is mostly observed in the inductance part. So we didn't observe what you're just talking about.
We're going to find what the circuits respond. So the circuits respond, I think you also have to do the other part. You have to estimate what the resistance change and what the capacitor change, because I think that is what this problem is really about. They mentioned three objects that you have to put in the circuit. So I think that if you want to really fit what this wants to say, you still have to do the two estimation of resistance and capacitor, and also the phase difference that I just mentioned.
Okay.
Okay, and okay, so you say that the phase you say you notice okay, so in the formula that you just answered, you say that the L times the RDT is the value of the whole system. But after you put the metal rod inside, is that thing going to change?
Sorry.
Is the thing at the left inside the V, the voltage, will going to be changed after you put a rod in the inductor?
We can actually say that the voltage will change. So since we are using our circuit driven by an AC source, so the voltage is keep changing. So what we can say is that after we inserted the rod into the coil, and we can say that the peak-to-peak voltage is changing.
Okay, thank you. Please summarize.
Okay, and this is my summary of the discussion. And for the theoretical part, we talk about the relationship between the resistance inductor, current voltage in the RLC circuit. And the experiment is set up. We talk about if the rod in the inductor will shake or not, and the reporter said he didn't really observe this phenomenon. And we also talk about the magnet output inductor will affect the magnetic field or not. I think it will affect, but he thinks that is not the main thing that we have to be focused on at this problem. And also the magnet's property in the experiment, but the reporter thinks that it is not important. So yeah, we don't really about data. We talk about the data comparison, and then of the data about RLC that the experiment setup stays very clear. Thank you.
Okay, thank you. Reviewer, please ask questions.
Okay, so I want to ask the reporter, and how did you measure the radius?
The radius of what?
Of the magnet?
You mean the inductance of the coil part? So basically, is a real item in reality, so we can just measure it by a ruler.
Okay, so in this figure, how where is your, which side is your x-axis and which side is your y-axis?
What?
The x-axis and y-axis. The x-y.
You mean the definition of the x and y?
Yes.
I believe that the x part is as the time goes, so x part represented time, and the y part, so you can see here, stage3 is talking about voltage. So I believe that the y part is voltage.
Okay, so for the opponent, then you measure that, you talk about the shaking of the inductor. So what do you think, if it shake, what will it affect the experiment?
No, when I say shaking, it's not a shaking that will be an experiment error. My shaking is that will it be a phenomenon that you will happen. And that is a phenomenon.
Okay, that's it.
Okay, thank you. Preparation time for reviewer. Please. Review, please.
So I'm going to figure, and this is our problem statement. And the reporter's performance is the strength is the strong evidence to prove the result of the theory, well understanding of the experiment theory. And didn't consider other force that affects the real situation. This is the suggestion. And they have to add the x and the y-axis into the chart. And so it should make the conclusion of the experiments more detailed by connecting it with theories. And the opponent's performance. The strength is the opponent highlights the point that the reporter did not clarity and explain enough. And the opponent's questions are direct and points out the unclear points that the reporter mentions. The weakness of the opponent is that they did not ask questions that did delve deep into the phenomenon. And she did not question the process and accuracy of the experiments. So for the discussions, at the beginning, the opponent asked for the theory, and the reporter answered it clearly by explaining the reporter answered it clearly. That's it.
Okay, thank you. Please give a concluding remark.
So first, I would like to thank for the suggestion from the opponent and the reviewer. So let us begin with my concluding remarks. So here's the summary of my report. So first, larger inductance values will have smaller amplitudes of voltage, and copper is weakly repelled by the magnetic field, while ferromagnets and magnets are attracted by the magnetic field, since copper is a non-magnetic substance. And third, with more parts of magnets inserted, the inductance will be larger, thus the amplitude of voltage will get smaller as well. So here's my clarifications. First, as the opponent asked, the definition of the evidence is actually the extending concept of resistance to alternating current circuits. And second, the shaking of the rod is only a phenomenon that can be observed, but it has, I can say it has nothing to do with the experiment. But rather than saying that it affects the experiment, maybe we can say that it's because the changes of the experiment parameters that causes this phenomenon. And here's the room for improvement of my experiment. So, as the opponents for the opponent's suggestion, I can do is that we can observe more parts of the entire RLC circuits and discover more details. And that's all. Thanks.
Okay, thank you. Yeah, please. Questions from viewers, please. Please.
I have a question for first for the motor. Obviously, you use the alternating current as the power source. So what is the frequency you use in your experiment? The frequency.
So here, the frequency is 30,000 hertz.
All right. So now the question goes to maybe the opponent first, and then the reviewer. Does that frequency matter? Do you think it is a good choice, or maybe you have some other comments? Do you think we need to worry about the frequency used?
No, I don't think so.
How about reviewer?
I don't think so.
Thank you. Yes, please.
So I understand what you try to explain. You mean like a frequency of 30,000 hertz is like it's too fast for us to.
No, that's what I mean. I'm saying, have you ever? Did you use any other frequency? This is the only one.
Yes, it's
the only one. It's a fixed number, right?
yes.
So what I'm saying is that why do you choose that particular value? Randomly or for some reason?
So it's kind of like is more convenient for observation of
Thank you.
Any more questions? Do you mind turn to the page number 4? Oh, okay. In here, there are several parameters. For example, resistance, capacitance, and also there's a value of L, the inductance. Inductance, right? So in your experiment, you put non-magnetic and ferromagnetic rod into the coil,
Yes.
inductance coil, right? So do you expect there is any change of the inductance?
So we generally expect that as we insert the ferromagnetic magnetic rod, the inductance will change.
Inductance will change. So that will change, I mean, for example, the non-magnetic and ferromagnetic, how do they change? That's my question.
Oh, so here the ferromagnetic. What's the difference from ferromagnetic and non-magnetic is that a ferromagnetic rod will generate an eddy currents in the inductance, which means it causes some reluctance to the inductance.
And how about magnetic, ferromagnetic? Ferromagnetic and also non-magnetic.
You mean?
One is ferromagnetic, the other one is non-magnetic. It's two rods, right? Two different rods.
Yes.
So in here you are only talking about the ferromagnetic.
So a non-magnetic rod like copper, they are not actually a conductivity, so there's no responses to.
So copper is not conductive. Okay, let's go to the reviewer, please. Do you understand my question? You see, could you go to the page number 4 again? Okay, they put magnetic rod, a ferromagnetic rod and non-magnetic rod into the inductor, right? So that will change the magnetic response and also electrical response, right? What's the difference? What's the difference? I mean, what's the inductance will change? The inductance will change, right? Okay, so can I move to the opponent?
I think that if we put ferromagnetic rod inside, the inductance will change, but if we put non-magnetic inside, the inductance will not change.
Okay.
Sorry, I have to correct what I just said. What I just said is that copper is not a conductive, and what I really mean is that copper is non-magnetic. So like it won't has the phenomenon of my explanation won't happen if we insert the copper.
Okay. Thank you. Thank you. Any more questions? Thank you. So, Juror, please give the score for the reporter. 5, 4, 5, 6, and 5. The score for the opponent: 6, 5, 5, 6, and 5. And the score for the reviewer: 5, 4, 5, 4, and 2. Okay, thank you.